Hi again, and welcome to episode 3. I'm Olivia, and this is Lily, and we're both students at Dartmouth College studying earth science. Today, we're in New Hampshire looking at glacial moraines that were deposited thousands of years ago as the last ice age ended. We're filming this in 2023 at the end of what has been the hottest summer on record. In this episode, we will look at how a warming planet thousands of years ago impacted the huge ice sheets that covered much of the northern hemisphere. Determining how the stability of ice sheets changed as the planet warmed in the past should give us a good idea of how ice sheets like Greenland and Antarctica might respond to rapid human-caused warming today. With that, let's join Dr. Meredith Kelly from Dartmouth as she uses the ridges and plains that we studied in episode 2 to better understand how our ice sheets might respond in a warmer future.
So one really neat thing about these landforms is they represent completely different environments. So the esker sediment, or the fast-flowing stream sediment, was deposited beneath the ice sheet. And the barbs, or the lake sediments, the lake floor, was deposited in a lake after the ice sheet had retreated through this area. And this is some really interesting and important information. So I'm going to show you a picture of an outcrop, and this is from a different area where we actually see these types of sediments in the same exact location. Okay, so at the bottom of the outcrop you can see there are coarse grain sediments. These look more like the esker, the stream sediments. They're big grains, they're big clasts in there, and this was actually material that was deposited underneath the ice sheet. Well, if you take your eyes and look up through the outcrop, at the top of the outcrop, you know what these sediments are. We've looked at these. These are the lake sediments, the varbs. They're layered and they're very fine grained. And these were deposited in a lake in front of the ice sheet. So we could draw a line between those two sediment types in this outcrop. And that line is what geologists call a contact. And that contact is really neat. That actually represents the time, or the exact moment when an ice sheet retreated or receded through an area. So that environment in that location changed from being underneath the ice sheet to being underneath a lake in front of the ice sheet. So there's been a lot of work done on finding the contact between subglacial sediments and overlying lake sediments throughout the Connecticut River Valley. And this contact's been found in a number of places. It's also possible to determine the time or the age of that contact using the varbs and a method known as radiocarbon dating. And with that method, we can actually say the time when the ice sheet retreated from an area. So for example, that contact in the Hanover area dates to about 14,000 years ago. That means that 14,000 years ago, Hanover went from being covered by a large ice sheet to being covered by a large lake. Now, finding this contact, the location, and being able to determine the age of it provides a really neat data set. And there's a professor at Tufts University named Jack Ridge who's done a lot of research on this and has found this contact in a number of locations in the Connecticut River Valley. And we're going to use the data that Jack has collected here. And we're actually going to use those data to plot location and age of these contacts and calculate the time or the rate of ice sheet retreat. So I'm going to hand you over here to Ron Hale, who's a science teacher in Chicago, and he's going to walk you through these calculations. I'm excited to see what you find, and then I'll be back to discuss this more with you after that. So have some fun with Ron.
Hello, my name is Ron Hale, and I'm from Chicago, Illinois. I teach 5th grade math and science here in Chicago. If you know anything about Chicago, it sits on the shores of Lake Michigan. Lake Michigan was carved out over 15,000 years ago by an ice sheet that covered this entire area. Over time, that ice sheet melted and retreated to the north, leaving behind the soil that I'm standing here on today. The same ice sheet that covered Chicago also covered the northeastern part of the United States around Dartmouth College. Today, we're going to see what we can learn about our climate future by analyzing how ice sheets retreated in the past. Specifically, we want to investigate how fast the ice sheets retreated at the end of the last ice age. Fortunately for us, the eskers and varves that Meredith introduced to us in episodes 1 and 2 actually provide the data we need to conduct this investigation. We're going to start in Springfield, Massachusetts. From there, head to Turner Falls, Massachusetts, and end in Claremont, New Hampshire. So let's take a look at the first of our 3 locations for today. If you can, in your science notebooks, construct 4 horizontal lines. At the top of our line, this will be our retreat rate calculation. Next to that will be our varve esker retreat evidence location. On our second line will be our retreat distance, followed by time to melt and retreat. And on our last line will be our calculated retreat rate. If we take a look at our map, we're going to look at 2 locations today, Springfield, Massachusetts, and head north up to Holyoke, Massachusetts. We know that ice retreated from this area approximately 17,000 years ago. We know the retreat distance from Springfield, Massachusetts to Holyoke, Massachusetts was about 13 kilometers or 13,000 meters. The time it took our ice to melt or retreat was about 350 years. And to calculate our calculated retreat, we need to take our distance, which was 13,000 meters, and divide it by the time it took, which was 350 years. And we know that ice retreated from Springfield, Massachusetts to Holyoke, Massachusetts at about 37 meters a year. So let's head over to our second location. We're going to head over to Turner Falls, Massachusetts. And if we take a look at our map, Turner Falls, Massachusetts, we're going to head up over to Charleston, New Hampshire. We know that ice retreated from this area approximately 15,000 years ago. As that ice retreated, it did so at a distance of 70 kilometers or 70,000 meters. We also know that the time our ice retreated was about 850 years. So what I would like to do is have you pause the video and see if you can calculate the retreat rate of our ice as it moved from Turner Falls, Massachusetts up to Charleston, New Hampshire. See you in a little bit. So how did you do? If we take a look at our distance of 70,000 meters and divide it by the time it took, which is 850 years, we know that our ice retreated from Turner Falls, Massachusetts to Charleston, New Hampshire at a rate of about 82 meters a year. So let's take a look at our third and final location of today. If we take a look at our map, we're going to head over to Claremont, New Hampshire, and head north from there to Littleton, New Hampshire. We know that ice retreated from this area approximately 14,000 years ago. We also know, as the ice retreated from Claremont, New Hampshire up to Littleton, New Hampshire, it did so at a distance of about 115 kilometers or 115,000 meters. We know that it took 400 years for our ice to melt. So at this time, I would like you to pause the video, take some time, use this data, and calculate our retreat rate of our ice as it retreated from Claremont, New Hampshire up to Littleton, New Hampshire. Check back in a little bit, see how you did. How did you do? We first needed to know our retreat distance. In this case, was 115 kilometers or 115,000 meters. We also needed to know the time it took for our ice to retreat, which was about 400 years. We take our distance, which in this case was 115,000 meters, and divide it by the time it took, which was 400 years. We should have come up with about 300 meters a year. So how did you do?
Thanks, Ron. Those data are super interesting, but I think they might be easier to understand if we make a graph. Let's put all 3 of these different retreat times into a graph. Let's put the retreat rate on the y-axis and the time on the x-axis. Since we're going back in time, We can start our graph on the left with 18,000 years ago and end it on the right with 13,000 years ago. Climate scientists usually label time this way as years before present. Go ahead and plot your data on the graph. When you're finished plotting the points, make sure to estimate a best fit line. Pause the video and come on back when you're done so that we can all compare our graphs. Welcome back. Here's what our graph and best fit line looks like. Hopefully we have similar looking graphs. It might be helpful to add a note to the graph to show how the temperature of the planet was changing during this period. Now let's take a second to think about your data. Please write down 2 things that you notice about your data and 1 thing that you still have a question about. When you're done with that, hit play again, and we can go ahead and finish things up with Meredith and Ron.
So the question we set out to investigate was, how fast did the ice sheet retreat at the end of the last ice age? Our data suggests that this question does not have a simple answer. Our data suggests that 17,000 years ago, the ice was retreating at a rate of around 37 meters per year. 15,000 years ago, it was retreating more than twice as fast. And 14,000 years ago, the ice was melting at an incredible rate of about 300 meters, or a distance of more than 3 football fields every year. What does this mean when we look at our climate future? For the answer to that question, let's go back to Meredith.
So, at the end of the last ice age, this large Laurentide ice sheet retreated from the south to the north, and much of this retreat was driven by a warming that inherently was caused by an increase in the amount of sunlight reaching the northern hemisphere, causing large ice sheets in North America and on Greenland and in Europe and Scandinavia to recede. But there are also large other climate changes going on at this time. These include changes in atmospheric greenhouse gases, such as carbon dioxide, and also a change in sea level. All the ice that was melting was contributing water to the ocean, causing global sea levels to rise. So we as scientists can use this incredible record of ice sheet retreat in the past in combination with records of climate, like records of temperature or carbon dioxide or sea level rise, and ask the question, what was causing, or was the ice sheet responding to other climate factors during the end of the last ice age? And Jack Ridge has done this. He has an incredible data set of ice sheet retreat through this area, through the Connecticut River Valley, and he's been able to compare that with records of past temperature that have been developed using ice from the Greenland ice sheet, long ice cores. And what he's been able to show is that this big increase in ice sheet retreat rate that you just calculated from less than 100 meters per year to greater than probably 300 meters a year that happened right around 14,000 years ago, that was associated with a big jump, a big increase in temperature that's registered in Greenland. So that tells us that even though there are these big ice sheets that seem like they would be these large systems to respond to rapid climate changes, rapid warmings, that they actually likely did respond to these rapid warmings. And that's really important for us to understand as scientists and for projecting future change, because we have large ice sheets on the planet now in Greenland and Antarctica. Together, the ice in these ice sheets could contribute as much as 70 to 80 meters of global sea level rise. And we're wondering what's going to happen with them in a warming world. And what we see in the past from studies like we've talked about here today, and that you've actually now done some great calculations, made some observations, made some calculations for, we can show that ice sheets in the past responded pretty rapidly and quickly to rapid climate change, and that's something that we need to be concerned about today with the modern ice sheets. So I hope this was fun. If you have questions, I'm happy to talk more. I'm always on email. I encourage you to check out Jack Ridge's data set, and take care. Thank you. And they have this really cool structure. Hold on one second, yes?
Are we going to go to the same place that I ran around and did cartwheels?
We can if you want.
I want to. I want to go to the circus.
Okay, GoPro stop.
So funny.
Tough one.
It
Showbiz.
is a tough one.
No joke.
Showbiz.